So this talk is about checkpointing the uncheckpointable. In some sense, this has been the central question in our research group for at least 15 years now. And as I get into the slides, you'll see more about what I mean by that. In particular, one of the big barriers to checkpointing is that when you do have large data, how can you save the state of that large data? We don't want to have to stop and save terabytes at each checkpoint. So sometimes I'm going to use the word snapshot versus checkpoint. When I say snapshot, I'm really thinking about saving the state of current RAM to memory or persistent memory to stable storage. However, checkpointing involves more than that, because if you want to restore, and if you have made kernel calls in the meantime, then you need to somehow simulate doing those same kernel calls again. Similarly, if you've been using a GPU, you may have to set the GPU state back to what it was, and so on. So, why do we need checkpointing anyway in HPC? So one obvious reason, and maybe the most common at the top here, is my application takes 1 week to run, and they only have a 48-hour batch allocation slot. So even though in the early days people kept saying, well, computer nodes can crash. If it crashes, you need to back up and from a checkpoint and then restart. In fact, the more common reason for which we're getting a lot of requests is simply a job that takes longer than a batch allocation slot. And the system administrators don't really have the flexibility to schedule jobs that will run for a week or more. So therefore, checkpointing is the one that mediates between the system administrator and the end user with a long-running job. Another obvious place where it saves the bacon for the system administrator is if there's an upcoming shutdown. So it could be unplanned for various reasons. For example, we've been working with NERSC in California, and at least twice in the last year, they had to shut down with little notice because there were forest fires, and the electric company was shutting down so as not to cause more forest fires. Next. So DMTCP, what does it stand for? Distributed Multi-Threaded Checkpointing. It handles distributed processes. It handles things like MPI for high performance computing. Obviously, it handles the multi-threading. We've had a lot of interactions with industry, as you can see, and of course, we have our standard academic support from the NSF, as is the case with, I think, most of the high quality academic projects. Next slide. Okay, so what is checkpointing anyway? So checkpoint restart is the ability to save a running application to disk, or now we would just say stable storage, and then to restart it. DMTCP is widely used for high performance computing. If you go to that link, you'll see at least 120 publications by other groups who are using DMTCP. These are refereed publications, and by now it's probably larger. I haven't done a scan of the literature recently. We handle the things that you'd expect. You can do periodic checkpointing. Under program control, you can decide when to checkpoint. You can manually checkpoint. The runtime overhead typically is less than 1%, so that tends not to be an issue. The idea here is everything is transparent. We're always working above the POSIX interface, and I'll say a little more about that soon. And then, especially important, the second bullet from the last, we have plugins where the end user can add their own plugins for added flexibility. So if you want to add a new subsystem that's, say, not MPI, not CUDA for GPUs, maybe it's a special file system, maybe it's a new persistent memory system. We talked about DAOS from Intel. So in each of these cases, you would just write another plugin in which you basically spy on the executing process to see what happens to the subsystem. And then at the time of checkpoint, you save all the parameters of that subsystem. At restart, you would restart it. So while we don't have access currently to Deos, I expect we could easily support Deos also using our idea of plugins. So this is a very powerful idea. Plugins come in many flavors, but this is a very high-powered version, which we think also adds to the uniqueness of DMTCP. And then finally, we're working closely with the NERSC Supercomputing Center. Right now, it's the Cori computer there, Cray. And the idea there is to demonstrate how best to use this technology for and show best practices. Next slide. So, and next, let's say a little about the philosophy of DMTCP. So we believe that all of our work should be free and open source, although we work closely with industry on their own proprietary systems. There are some interesting anecdotes there if I had some more time to tell. But in any case, right now it's open source, LGPL. Purposely, it's non-contagious. We're also considering switching to Apache since some companies are more comfortable with that. We strongly believe in transparent checkpointing. We don't modify the application binaries. We don't modify the Linux kernel. To a large extent, we don't even need to use the procmaps file system of the Linux kernel. So everything is above, is almost entirely above the POSIX level for system calls. This gives us exceptional robustness because things can change underneath. And as long as they follow the POSIX standard, we don't have to adapt. It just works. So when there's a new version of the Linux kernel, it doesn't affect us. We just continue. New version of libc, it doesn't affect us. And there's synergy, of course, between what we do in academia and industry. So we've always believed in, on the one hand, publishing to get our academic credit, but at the same time, making a true impact on current practices in industry. So next slide. Good. So as I said, there's this one fundamental question that has been driving us through the entire 15 years of this project. What are the limits of transparent checkpointing? So at one point, the idea was, well, you run a batch job. The batch job should be primarily using the CPU, and you're done. And it doesn't need to interact with databases, doesn't need to interact with the web. And that's it, end of the story. But over time, as the industry has grown and new types of subsystems have evolved, we've also pushed to try to support those new subsystems to answer this fundamental question. So for example, MPI. MPI could be over the InfiniBand network or TCP network. We've supported that for quite a long while now. But now there are newer networks. So there's Cray GNI. This was in fact the impetus for us coming to work with NERSC, because previously they had support based on, well, because Cray GNI is not generally supported directly in terms of checkpointing. Now there are also things like HP Slingshot, Intel Omnipath, new extensions to InfiniBand, and so on. So in the last 2 years, we've managed to support this. And the way we support this is not by trying to write a new plugin for each possible network. That would drive us crazy. There's no way we have the kind of resources that people in industry have. So instead, we simply support the MPI level, and we have a plugin for MPI that I'll talk about soon. Similarly, GPUs have now become absolutely standard. In the top 500 supercomputers, I think it's well over 20% now and growing, are now using NVIDIA GPUs. So we have a solution for that also. And all of this, as I say, depends a lot on plugins. In essence, there are 3 ideas that we have for extending DMTCP to the new subsystems: plugins, virtual IDs, and split processes. And so while here I'm still talking about a lot of the history of DMTCP, I'll soon talk about persistent memory. And we view this as just one more of these challenges that we have, and we believe we can manage to handle just as we've handled these past challenges. Next slide. So on the next slide, we're going to be talking about checkpointing to stable storage as it comes up. And the idea of checkpointing to stable storage is that stable storage, for example, disk, is often a lot slower. I think soon we'll have the next slide. And thank you. And so at this point, there are two pieces to taking a checkpoint of an application so that we can transparently restart it. We can checkpoint at absolutely any point in the application. It can be doing, it doesn't matter what. And we just, when it's time, we pause all application processes and threads, save their state, and restart. As far as saving their state, the kernel and network status, well, that we can save in just a few seconds. That's never been a barrier. And we could probably do it even faster, but a few seconds seems to be fine for most people. The larger problem is saving the memory image to stable storage. And that, of course, depends on the bandwidth of storage. So originally it was disk, which was incredibly slow, 100 megabytes per second. Imagine trying to save a terabyte of active memory across many processes, perhaps in MPI. So SSDs made it faster. The nice thing about SSDs also is you can locate some SSD either locally on the compute node or else nearby. And now Optane gets us to the next level still. So this is something which we're really excited about. Originally, because of the long time to save to hard disk, this was the primary barrier for us to be widely used in high performance computing. It's precisely SSD and now especially Optane that's making a difference. So in any case, I tried to distinguish earlier between checkpointing and a snapshot. Snapshot has to do with saving the RAM to disk. It's problem number 2 on this slide with the 2 problems. But with copy on write file systems, we heard, for example, how Memberge is supporting copy on write. This now makes things a lot easier. So let's move to the next slide. And here we see persistent storage for persistent storage or persistent memory and HPC. So the persistent memory gets used at different levels. It could be a substitute for RAM. It might be a local burst buffer on that compute node. It could be an intermediate level in the storage hierarchy. But the idea here is that while a lot of this is still very new, we believe that we can rapidly generate DMTCP plugins that will model this hardware environment and then basically be able to restore that same hardware environment on restart. So the secret is in the plugins. So I'm going to say a little more about the internals of DMTCP to make this statement more believable. Otherwise, I could just stop the talk here and I claim we can do it, we're done. But let's see if we can convince you a little better. Next slide. Good. So this is the internals of DMTCP. Ultimately, we have a central coordinator. You need that if you're going to have distributed processes. It could be even a tree of coordinators. That's a detail. But in any case, when it's time to checkpoint, you tell the coordinator it's time to checkpoint, or maybe your application sent a message to the coordinator it's time to checkpoint. The messages come down perhaps through a socket. We've inserted a checkpoint thread inside each end user process. We can do that because we insert our own library into each end user process, and that library prior to main will capture control and create the checkpoint thread. It will also create a signal handler. Here in this example, it's SIGUSER2. And at that point, when it's time to checkpoint, the checkpoint thread just sends this signal to each user thread. The user thread is paused. Now that the user thread is paused, now we can safely copy all of user memory out to stable storage. So next slide. So here, let's go through perhaps three examples of what gives us the flexibility that we have. So for plugins, here we just see that we have a certain hierarchy of plugins. These are internals. The end user doesn't really need to worry about it. So let's move on to the next slide. And now we can get to some of the crux of the matter. So part of the idea of using plugins is we can create a virtual ID. This is very important because when we checkpoint on one system, we might want to restart on a completely different machine or even a completely different cluster. So whatever IDs we happen to be using have no validity on the new machine, whatever they are. They could be network IDs, it could be something related to namespaces, who knows. So let's take an example where we just want to worry about process IDs. As I said, we want to be completely transparent. So we're not going to modify the kernel. We're not going to, on restart, we're not going to tell the kernel, give us back the process ID that we started with. That's dangerous because maybe somebody else is already using that process ID. So we have to do everything above the level of the POSIX interface. So we have the actual process ID and a virtual process ID. Here we have four virtual process IDs, 4000 and 4001. And anytime any system call is related to a process ID, we interpose on that system call. So the joke is never let a user find out what their real process ID is. So here on that vertical dotted line, that's our plugin interposing at runtime. This is usually very fast. Ultimately, we're just looking things up in a translation table. So our plugin in that translation table will have recorded that the user asked for process ID 2652. We told the user, well, you now have process ID 4000 instead. Next one is 4001. Then when it's time to checkpoint, on restart, we now have a completely different process ID. So we ask the kernel, okay, what's my new process ID? And then we update that translation table. The memory image of the user process does not change at all. The memory image of that user process, wherever that user might have saved process ID 4000, we don't care. They still have virtual process ID 4000. For them, nothing has changed. It's only when they make a system call that we'll do the proper translation. Next slide, please. So that idea of virtual process IDs had basically, it answers why we have been able to be successful, say, for the last 10 years, and why there are many other groups that have adopted DMTCP for their projects. But now, just in the last year or two, we have still another idea. This comes back to this problem that there are many newer networks, and if we want to support MPI, we don't want to build a plugin for each new network that is developed. We could never keep up. So we needed a cleaner design in which we find exactly the right place to interpose at. And we've chosen, let's interpose at the level of the MPI call itself. And in this way, we can support any MPI that follows the MPI standard. Just as we obey the POSIX standard for libc, we want to obey the MPI standard for MPI libraries. And now anybody can create a new MPI, but as long as they follow the standard, they will find that we can checkpoint their MPI just fine. So in this picture, we have what we call a split process. It's an analogy with what happens inside the kernel in a device driver. In a device driver, they might have an upper half of the device and a lower half of the device. So in this case, we imagine that there's a lower half program, in this case, the MPI library. And previously, at the time of checkpoint, because the MPI library was in RAM, we would have tried to save that library and save its state. But that's problematic because that library could be using any kind of network, and we don't want to support every network that's ever been invented. So now the idea is when it's time to checkpoint, we are going to throw away all memory associated with that MPI library completely. We'll just get rid of it. So we're going to tag all of memory. Any region of memory will be tagged as either upper half, associated with the end user code for the MPI application, or it will be tagged as lower half, MPI library, network library, lower level libc, and so on. And then at checkpoint time, we save the memory in the upper half only. And then at the time of restart, before we worry about restoring the MPI application, we first have to worry about restoring MPI. Well, if there were 100 MPI ranks, then we just start a trivial application for MPI, which will have 100 MPI ranks. Now that we have a trivial MPI application with 100 MPI ranks, each individual MPI process with that rank looks through the checkpoint images to find where, so if I am rank number 17, where is my checkpoint image number 17? And then it restores checkpoint image number 17. We then connect the plumbing between the upper half and the lower half. And so on restart, what began as a trivial MPI application doing almost nothing automatically reverts to the original MPI application, and it can continue execution. And again, the key idea is we don't care about what kind of low-level libraries were used by MPI. It's irrelevant. We interpose only at the MPI standard. Next slide, please. So this seemed to work well, and this was the impetus for our collaboration with NERSC, since NERSC was using the Cray GNI library. And as far as we know, no one has ever been able to directly checkpoint the Cray GNI library, at least not in the transparent sense that we were interested in. So then we noticed, well, of course, applications are using CUDA more and more. So let's see if we can repeat this with CUDA using split processes. And as you'll see, the moral of this story is now we're wondering maybe split processes solves everything. In fact, we're now in discussions with Memberge about whether this idea of split processes can also be used even to support graphics libraries. But that's for the future. This, right now, let's go back to the CUDA library. So here again, we have the lower half, the upper half. The CUDA library is in the lower half. There in the middle, in blue, you see an array of function pointers, and that's the plumbing. So whenever the CUDA application makes a call to the CUDA library, it actually goes through to that array of function pointers, which points to where the CUDA library actually is. So then when we restart, we'll play the same game again. We'll start a completely new CUDA library that knows nothing about this application. And we can connect the plumbing because, again, we'll do it through this array of function pointers that we have here, just as we did something similar in the case of MANA. So the upper half application is linked using the normal NVIDIA linking scheme. We don't interfere at all, except now they're going to link with the CUDA stub library that we created instead of the actual CUDA library. And that stub library will then connect up. Next slide, please. Okay, so I think this gives you a lot of the idea about where we are and where we're going. As I say, we haven't had the chance yet to really work with persistent memory. We've seen it in burst buffers, but a lot of times it's just transparent to the application. So there's nothing extra for us to do. But in the newer uses of persistent memory, perhaps Deos and so on, now we see an opportunity to bring back this idea of plugins and even split processes, where the persistent memory subsystem will be in the lower half. And as I said, we can just throw it away and replace it in the upper half. In fact, in principle, we could even port between a system that uses persistent memory and a system that does not use persistent memory. Because as long as they follow a common interface, on restart, we could throw away perhaps the standard lower half and replace it with a persistent memory lower half. And with the right interface, we can still make everything work fine with plugins. As always in academia, a lot of this is based on the work of a lot of students, and also others from some research institutes who have visited our lab and started working with us. And then I'd just like to take a moment to announce that we also have this Super Check 21 conference coming up. As it says, this will be the first international symposium on checkpointing for supercomputing. That's the beginning of February. That's in close collaboration with NERSC. If it were a physical conference, then it would have been located at NERSC, and we're very excited about that. So if you search on that, I encourage you all to register. It'll be over 2 half days, and we're expecting that this will launch a greater emphasis on the use of checkpointing for supercomputing. As I said, in the past, transparent checkpointing was considered less practical because the time to write to hard disk was very slow. SSDs have made that problem partly go away. Persistent memory will make our situation even better. So we're interested in looking to the future. And of course, we'd like to thank several of our current sponsors, the NSF, Intel, and Raytheon. Thank you.